Great, so we'll finish up section 9.2, okay, which is on a little bit more with polar. We're going to get into the graphing a little bit more. And we're also going to learn to convert between polar and parametric. Okay? What did we say earlier? Polar was really good for graphing. What kind of shapes? Circles. Polar is super easy to graph a circle. Right? So we're going to look at graphing some circles in polar. And then if we have time, I'll show you how to graph a line in polar. Polar is not the easiest, it's not the prettiest looking equation when you graph a line. Y equals mx plus b is probably the best way to graph a line. It's the simplest. So just remember, when you have a point in polar, they give you a radius, they give you an angle. Okay, so what I'm going to do is I'm going to graph the equation r equals 2. Right, so you might be looking at that and be like, well, usually we graph things that say y equals. Well, if it's r equals, that tells you you're graphing in polar. Right, so the first thing you have to do is change your mode to polar. And then once you change it to polar and you press y equals, now everything says r equals. And if you press this button, it's not going to do an x, it's not going to do a t, now it would do a theta. Right? So it would change to theta because in polar, that's what you use for a variable. Okay? And try to remember that because polar, you're thinking about angles. And for angles, we use the letter theta. All right, so can anybody give me a coordinate that would have an r value of 2? Any coordinate. There's infinitely many, as long as r is 2. Yeah?
Above 2, 0.
Yeah, 2. So you could do 2, 0. I'm assuming we're in degrees. So that would be a point, you go right 2 units, and then you don't move. Okay. What's another point with a radius of 2?
245 degrees.
Okay, so we've got 2, 45 degrees. So that would mean you go right 2, and then you go clockwise 45 degrees. Does anybody have a guess what this is going to look like when we sketch the whole thing? It's going to be a circle. You can graph any point you want as long as your radius is a 2. Okay, there's another one, 2. Now, what else could the number in front be? It could be a negative 2, but you're going to get the same points. Basically, you're just going to get a bunch of points all around the circle. Okay? And when you graph it, we're going to get a circle of radius 2. Okay? So just type in r equals 2. I'm going to hit graph. And I'm going to take a look at what's going on. All right, so first of all, I might want to zoom in a little bit because my screen only needs to go, really, say, -3 to 3. And we'll also do that on the y's. Oops. -3 to 3. And what do you think theta step is?
How many times height places the point?
Yeah, it's just like t-step. So basically what this is going to do is plug in values from 0 to 6.28, okay? And it's going to go by 0.13s. Now, does anybody see what's wrong? Because if I hit graph, I'm not really going to get much of a picture at all.
Is it the max?
I just drew something right there, and that was it.
Is that the max angle that it's going to right now? Is 6.28?
There's something wrong with theta max.
It's not 360.
It's not 360. That number would be fine if this said radians, but it says degrees. So if you want to see the whole thing and you're in degrees, you need to set it to 360. And going by 0.13, it's going to graph thousands of points. So really, if you want to go 0 to 360, you could probably even go by 5s. 0, 5, 10, 15, and I still think it'll look pretty smooth. Now it is a circle because you can see it crosses the second tick mark on each axis. So it's definitely a radius of 2 in all directions. But how can I make it look circular?
Zoom 5.
Yeah, if you do zoom 5 after you do what I just did, it'll make it so it doesn't look distorted. And there's your picture. So actually, I'm just going to go like that. Okay, so any questions on graphing the equation r equals 2? All right, let's try theta equals 2. Now, just like when you do y equals mx, or y equals, okay, can the calculator do x equals? Like if I wanted to graph that, can the calculator do it?
Yeah, not in like this form.
Well, even if I change back to function, when you change to function and then you press this button in the upper left,
Well, yeah.
what does it say right there?
Oh, y.
It says y. I can't change that. Okay? So when you're graphing as a function, it's always y equals. This is not something that's possible to graph on the calculator. Neither is this. Right? I can't graph theta equals. It's always r equals. Okay? For the same reason.
Well, yeah, that makes sense because like you wouldn't even know where you're graphing pretty much. If it was to-
Yeah, you couldn't. Yeah, you can't graph that. So can somebody give me a coordinate that has an angle of? Let's pretend that's in radians. What would be a coordinate that has an angle of 2 radians? 1, 2. Okay. What's another one? 2, 2. Okay. What's another one? 3, 2. Another one.
4, 2.
So I'm looking for seeing if somebody says something a little different.
10, 2.
Okay.
Pi something.
10, 2, 3.14, comma 2. Okay, those are all okay. What else?
0,
0, 2. Okay. Keep going.
-1, 2.
-1, 2. So we can have negatives as well. So 2 radians, that's about, let me just see how many degrees that is. So that's 2 radians, just to get an idea of where I should be on the graph. I'm going to multiply by 180 and divide by pi just to kind of see what it comes out to. So it's 360 divided by pi. It's about 114 degrees. Okay, so that's roughly what 2 is, 114 degrees. So if this is 90, it's a little past that. So let's start with 1, 2. So we go 1, and then 114 degrees. 2, 2. So we go right 2, and then 114 degrees. Okay, 3, 2.
Nice.
Going to be on the third circle, 114 degrees. And then if you did a negative, -1, 2 would bring you down there. Okay? You would go 90, and then you'd have to go a little bit past it. So what kind of shape am I getting here?
A line.
Yeah, a line through the origin isn't really bad to write the equation for. It's just theta equals, and then a number. Okay, so that's, let me fix that. More like that. Okay, not too bad. But that's still something you cannot graph on the calculator. Where when you do y equals mx plus b, we can graph lines through the origin super easy. Okay, you just set your y-intercept to 0. Type in y equals 2x, and you get a line right through the origin. Okay, but you can't graph that in polar on your calculator. Okay, so if you've got to figure out something you can't graph, just make up some points, right? The radius can be anything, but the angle has to always be a 2. And don't forget to think about negatives, because if you don't deal with negatives, then your line would only go in one direction from the origin. Okay? Okay, any questions on that? Okay, so a couple basic graphs. Right. The next thing we're going to graph is this one. Okay. And it's a little tricky to graph, so we're going to think about graphing this kind of in different sections. Okay, like one part at a time. And we're going to make a table. I think a table will be the easiest way to graph it. Okay, I will give you a hint about the graph. Everything in this that we're going to draw here is curved. Okay, there are no straight segments to this picture. It's all curved. All right, so first I just want to try to remember a little bit about sine. Okay, if we draw a sine, it looks like this. Okay, and there are 4 basic sections in this graph. Okay, if you kind of want to think about it like from here to here, that's one section. It's going up. Okay, the next section from here to here. Okay, it's going down. And then it hits the axis. Okay, in the third section, it's going down till it hits its lowest value. And then in the fourth section, I'll just leave that one in black, it's going back up again. Okay. If we were to think about these in degrees, where does the first section end? 90. Or if you're thinking about it in radians, pi over 2. How about the second section? 180. Or pi. The third section? It ends at 270. And the fourth section, we're at 360. Right? So we're going to think about what happens in the blue, the green, the red, and the black section. Okay? Just by looking at that picture. Oh, I already had that. Well, I like my colored one better anyway. So let's think about the radius here. Okay? This is a repeating function. What I just circled is periodic. Okay? It's going to have a minimum value and a maximum value, and it's just going to keep oscillating back and forth between the two. What's the smallest that sine can ever be? -1 times 3 plus 3. 0. So the smallest radius that this picture is going to have at some point is going to be 0. And the biggest it could be, well, is when sine is the biggest. What? 6. Sine could be 1 times 3 plus 3. So when we draw this picture, it's going to be a picture of something that has a radius from 0 to 6. But the radius is constantly going to be changing. Sometimes the radius will be 0. At another point, it might be 2.5. It's changing. Okay? But it's not a spiral, okay, which has a changing radius. All right. So what we're going to do is we're going to look at what happens to sine over each of the 4 intervals that we just described. And then we'll look at how does that affect the whole graph. Okay, so first we'll just focus on the sine, and then we'll look at the whole thing. All right, so let's start from 0 to pi over 2. What's happening to my y values? What do they start at in that first section of sine? They start at 0. And what do they head towards and finally end up at that first section? That's the x value.
Oh, sorry,
1. Hey, let's fill all these out. What about from pi over 2 to pi? The y values start at what and head towards what?
1 to 0.
Heads from 1 to 0. How about from pi to 3 pi over 2?
From 0 to -1.
Starts at 0, heads towards its lowest, and then what about in the last section?
From -1 to 0.
-1, back to 0, and now we're back at the beginning again, and it's going to repeat. Okay, so now let's look at the effect of how sine is going to affect the whole thing. So, all I'm going to do is take each number, 0 and 1, and then plug them in where I just circled. And that's going to tell me what the radius is going to do from its start to its end. So, if the sine comes out to 0, which that's where it starts, What's 0 times 3? 0 plus 3. So in this section, when we draw the picture, the radius starts at 3. And then, let's see what happens. If sine is 1, what's 1 times 3? And then plus 3. So in this section, the radius is going to grow from 3 to 6.
It kind of reminds me of like the vertical shift, horizontal shift stuff.
The shifts? Yep. Yeah, we'll talk a little bit about some shifts too. Okay, let's look at the next section. The radius is starting at, the sine is starting at 1.
6.
So the radius in this section, it always has to pick up where the last section left off. Always. Those numbers are always the same. So it's going to start at 6, and sine is going to head towards 0, which means the radius will head towards 3.
You can pretty much fill the rest out like pretty easily.
Okay, yep, and then in the third section, sine is going to start at 0, which means my radius starts at 3. And then sine is going to head towards -1. So if sine is -1, what does the radius become?
3. Oh,
Zero.
0. What's -1 times 3?
3 plus negative
Yeah. So in that section, the radius is getting smaller, starting at 3, and it's going to shrink all the way to 0. And then the last section, where's the radius going to start in this section? It's going to start at 0, and it has to go back to 3, so it's going to pick up back where it left off. Okay, so I'm going to try to draw that, and I'm going to draw everything curved. Okay, so let's see what we can do. So in the section from 0 to 90, the radius starts at 3. So when my angle is 0, my radius starts at 3. And by the time I get to 90, the radius is going to grow to what number? 6. So the radius is growing over this section. So it's going to look kind of like this. And notice as you move along, the radius is getting longer and longer as you move from 0 to 90. Each line segment that I drew is a little bit longer than the one before. I'm not going to leave those lines in there, but that's the idea. Okay. Any questions on that? Now, let's look at what's happening from 90 to 180. What's happening to the radius in the second section?
back down to 3.
It's shrinking from 6 to 3, and it's going to be symmetrical to what we just did on the right. So what I'm going to actually do is just copy this and reflect it. Doesn't quite line up perfect, but that's okay. So now the radius is starting out at 6, and each line that you draw to the curve is getting shorter and shorter and shorter, until finally it gets to its shortest point in this section, which is 3. Okay. Whoops, let me do that. Okay, next section. What's happening from 180 to 270 to my radius? It's going from 3. It starts at 3, and it's going to shrink to 0, which means eventually it's going to touch that spot right there. So what that's going to kind of look like, something like that. So my radius starts at 3, and it gets shorter and shorter and shorter each time. And then the other side is a mirror image. It's growing from 0 back to 3. Okay, so my drawing isn't perfect, but you can kind of see what it's supposed to look like.
An upside down.
Yeah, in this case, it's kind of like an upside down heart. And the fact that it looks like that, that's where it gets its name from. Okay? That shape is called a cardioid. So now, anytime you see something of this form, a plus or minus a sine theta, or change the sign to cosine, a plus or minus a cosine theta. Anything that looks like that is a cardioid. So when you're graphing things in polar, it's easier if you can kind of remember things you've graphed before and the pattern they had, so then you don't have to think about it as much. Okay, so if I go back and look at the equation I just graphed, 3 plus 3 sine theta. That's exactly what this is. 3 plus 3 sine theta. That's a cardioid. Okay? You just have to keep these two numbers the same. If you make them different, weird things will start to happen to it. You'll get different graphs that are not cardioids. Okay? So let's type in 3 plus 3 sine theta and see what the calculator does. Keep in mind that the calculator is going to distort the picture, so it's going to make it look stretched out a little bit. Now, to get a full picture of the cardioid, what does theta have to go from? It's got to go 0 to 360. If it didn't go to 360, it wouldn't draw the whole thing. If you went beyond 360, it would start tracing over what you already have. Okay, so I'm going to go 0 to 360. Is my window big enough?
No.
No. If you go back and look at the picture, I have to go at least to 6 on the y-axis. I don't really have to go that big on the negative y-axis or the x-axis. But the positive y-axis has to go at least to 6. Okay, so I'll go to 8. Let's see, -4 to 4, that should be fine. So we'll get a picture. And I think mine looks a little more like a heart. If you change the zoom to make it square, it'll look a little more like a heart. But I tried to exaggerate it a little bit to make it obvious that it was a heart. I don't know if you would have guessed that was a heart. Probably not. Yeah. And notice in here how it's drawing it kind of straight. That's because my t-step was 5. Okay? If you make the t-step a little smaller, or theta step, now I bet it won't look as straight by the origin. It'll look a little more curved. A little bit. I think it looks a little more curved. Okay? Now, I said to you that these two numbers had to be the same. Okay? If you make one of them different, okay, watch what happens. Okay. You get the same basic shape, but that time it didn't go to the origin. Okay? Now let's try it the other way. Okay. If you change that number, okay, watch what happens this time.
Is it still a cardioid if it doesn't go to the origin?
No. Okay, so what happens here is the middle part actually loops back on itself. Yep. Okay, so you can change all these things, but according to our book, the definition of a cardioid, those two numbers have to be the same. Now, if you type it in with cosine, what's the difference between sine and cosine in terms of like transformations? Yeah, when you graph sine and cosine, they almost look the same, right?
Oh yeah,
But one of them is...
starts, like, it's just like reverse. It's like if you flip it, you flip sine, right?
No, it's like if you move side over,
Yeah, if you move it over...
over 2.
Yes, exactly. It's a phase shift of 90 degrees between sine and cosine. So, if you change sine to cosine, what's going to happen is everything is going to be shifted 90 degrees. So it's going to do a quarter turn. So now the heart is just going to face a different way. I didn't adjust my window, so it might go off the screen, I'm not sure. A little bit. But you get the idea. Okay, so if you change sine to cosine, it turns at 90 degrees. All right. But that's still a cardioid. It's just now it's on its side.
What do you want to turn upside down, Mr. Hager?
If you wanted to turn it upside down,
Inverse sine?
I did tangent and it looks funny.
nope, you'd still have to keep it as sine or cosine.
Yeah.
But what could you do to rotate this a little more? What could you change?
Theta,
Theta. What could you put in there?
90 or negative 90.
Yeah, if you did a plus 90, that's going to rotate it another 90. So now the heart is
Yeah, kind of like a real heart now.
facing a different way.
Yeah, ooh.
Okay. And you could change this number to anything you want. And it's just going to rotate it that many degrees. Okay, so now it's on a 45-degree angle now. Yep. So you can play around with different things and see how it changes the graph. But remember to set your theta max to 360 in degrees or 2 pi in radians. All right, so next thing we're going to look at is how we can convert a polar equation into rectangular. Okay. Polar is r equals something. Rectangular is usually y equals something. That's what we're doing. Yeah, and we kind of did this yesterday. We didn't do it with equations. We did it with individual coordinates, but we used the same formulas. We know that if you want to change x to polar, we had this formula r cosine theta, and we had the formula for y, which was r sine theta. Okay. These are all the formulas we had yesterday that gave us relationships between rectangular to polar and polar to rectangular. So we're going to use all the same formulas again. Okay, so the first thing I'm going to do is I'm going to convert a cardioid into a rectangular equation. Now, does a cardioid pass the vertical line test? No. So
Sadly.
a cardioid is not a shape you can draw in this form on the calculator. We can write it, but it's not something you'd ever be able to type in. Okay, if you want to graph a cardioid, you have to do it in polar. Okay, so using what we have here, basically you just use substitution. You have to change everything in this bottom equation till you get rid of all the r's and all the thetas. Because if you want rectangular, the only letters you're allowed to have are x's and y's. So what's something in that equation that I can't keep if it's got to be in rectangular?
Sine.
Sine of theta. So I'm going to look up above and see, do I have a formula that involves sine?
Yeah, y equals r sine theta.
Yeah, y equals r sine theta. Now, I want to plug in for this. So what would sine of theta equal if I rewrote that equation? I don't want to know what y equals. What would sine of theta equal? Y over r. Okay, just rearranging the equation I underlined in red.
Zero.
Any questions why sine is y over r?
Yeah, can you just like go over it?
So we just, to get sine by itself in this
I
equation,
see it, yeah, you just, okay.
just divide each side by r.
That was,
Now plug that in right there. And that's going to get rid of the sine. We're converting sine to y over r. Okay, so I've got r equals 3 plus 3. And let's write it, yeah, let's write it like this. Y over R. Questions on what we just did there? Okay, now the next thing is, this fraction is going to be kind of a pain to work with, so if we can get rid of that denominator, that would be nice. What could you multiply everything by to get rid of the denominator of R? R. So multiply by R, R, and R. That's gone. And what does my equation become now?
R squared equals 3R plus 3.
Plus
Y.
3y. Is there anything there that it's okay to leave it if we're for our final answer? Anything that's fine the way it is right now?
Y.
The 3y is fine. X's and y's in the final answer are fine. R's are not. So now I'm going to look at each thing here and see, do I have a formula for r squared? Can I replace that with anything? I'm going to replace r squared with x squared plus y squared. So I just got rid of the r's there. And now, if this is r squared, what could I plug in for r?
X plus Y.
Careful, not quite.
Well,
So if we know r squared, then we know r too.
X plus Y.
No, that's what James said.
as
X to that line.
X minus Y.
I wrote that wrong. That's r and x. So how would you get r by itself there? You could put x squared plus y squared or y squared plus x squared. It doesn't matter. Take the square root of both sides. And now what's the rule when you do that? What happens on the left?
Well, it cancels out.
That becomes an r. What about on the right?
It also
Y.
Nothing cancels there. You can't. If you had something like this, the answer is not 3 plus 2. Try it. You won't get the right answer. You can't do anything with that. You just have to leave it. So all you can do is just leave it as the square root of x squared plus y squared, or y squared plus x squared. I'll keep it in the same order we've been doing it. Okay? But you cannot simplify square roots when you have addition or subtraction. Only if it's multiplication then. Okay, so I think somebody said that right away, but they were canceling the square and the square root. You just can't do that. So just overthinking it a little bit, just leave it like that. So we got rid of the r squared. 3 is fine. We got rid of the r. 3 is fine. And y is fine. So that is a cardioid in y and x form. Again, it's not something you can graph because there's no way you're ever going to get y by itself here. It's not possible. Right? So that's why we use polar, because the equation looks a lot nicer. But that's how you change polar to rectangular. Okay, I would never ask you to graph that, though. I would ask you to graph a cardioid in polar, but not like that.
Can you still add like the first part where you use the y equals r sine theta? Is that what you do there?
So we changed sine theta using the formula I underlined in red. So we solved for sine by moving r to the other side.
Okay.
Yep.
So we should probably write those down, huh?
You already have those. Those were, I think we did them yesterday. Yep. Just like this one, you could solve that for cosine if you wanted. Cosine would be x divided by r. Okay. You could solve this one for r. That's exactly what we did in this problem. R is the square root of x squared plus y squared. So you can rearrange these formulas. We didn't use this one. We didn't need it. A lot of times you don't need it. Okay? So it's really, this kind of stuff, it's just substitution, plugging in one thing for another thing till you get rid of everything that's not an x or a y. And numbers are fine too. You can leave numbers. All right, so the next thing, it's a little bit easier than the last thing we just did, is how can you graph a polar equation in what we learned yesterday, or 2 days ago, parametric. So now I'm going to show you how to graph something in polar to parametric. All right, so suppose that you have a function in polar. Okay, they'll give you a formula. R equals something. Okay, in the problem that I'm going to do with you, it's going to be R equals 7 sine 2 theta. So they'll give you a formula. All you have to do, if you want to graph something that's polar, and you want to do it in parametric, is first thing you have to change your letters. In polar, we use theta. In parametric, what letter do you use?
T.
T. So you change all your thetas to t's. And that's what I've tried to write right here. Okay. The next thing, okay, after you do that, you take whatever your function is, okay, whatever they give you, right here, and you write it right here with a cosine next to it. That's the x part. Then you take whatever your function is, after you change things to t's, and you put a sign next to it. And that's the y part. The reason this works is because remember when we studied vectors or anything where you take a point, make a triangle, and break it into its components. The x component always has to do with cosine. So it's like you're taking just the x component. And the y component always has to do with sine. Right? So you're taking something that's on like a diagonal and you're breaking it into two components. Just like we did with vectors. Same idea. Right? So again, take what they give you, change the variable to a t. If you put a cosine after it, that's the x part. If you put a sine after it, that's the y part. And that's multiplication. I just didn't write that. That's all.
What's the F?
What's the what? That's the function they gave you, whatever they gave you originally, but you change the variable to a t, just because you're doing parametric. So they're going to give you a function, change the variable to t and put times cosine. That's the x. And then put times sine, and that's the y. Okay, so here's our function. R equals 7 sine 2 theta. If I want to change it to parametric, what's the first step? Yep, to t. So I'm going to just take that and change it to t. Now, what we just wrote here, this represents kind of like something like this. It represents a point here. But that point has a separate x and a separate y value. How do we get just the x value of that number? What do you have to multiply it by? Well, let's look at this. If you wanted to separate, pretend that this is one point. Okay, this graph is made up of millions of points. Here's one of them, okay, right there. If you wanted to separate this into its components, what would you draw here?
Triangle.
You make a triangle. Okay. This would be the x component. This would be the y component. And this angle would be what letter in parametric?
Well, T.
T. There's your angle. Theta is what we normally call it, but in parametric we use T. So that's x, that's y. And now this, your hypotenuse, well, that would be your formula. Okay? We don't know what our exact value is because I didn't pick a value for T. I'm just drawing something kind of generic. But how would you find it? You would plug in a number for theta and calculate it out. You'd use your formula. That's what the hypotenuse is. It's the formula they gave you. So now, if you wanted just the cosine, just the x value, what trig function would you use? Okay, adjacent and, no, not opposite. It's always the hypotenuse, right? Because that's what you'd know. You could plug in a number and we could figure out what it is. If, pretend theta was 3. You could type it in and see what you get. So the cosine of t equals adjacent over your function. Okay, our function is 7 sine 2 theta. I just didn't write the whole thing out. That's our function. And now, how do you get the x by itself?
Just multiply by whatever's on the bottom.
Multiplied by whatever's on the bottom, which is our formula. So we would have our formula times cosine t. And now I told you the first step was to take your formula and change that to a t, which we've already done. So now we've got our formula. That part is that part. So now how do you get just the x value of that part? What do you have to multiply it by? By the cosine.
Plug it in, right?
And what would be our formula to find the y value of that point?
7 sine 2t.
Yep, you'd have to take 7 sine 2t. Okay? That's kind of the x and the y together. Now how would you separate the y component off? What would you multiply it by? You'd multiply it by sine. So that equation in polar and what we have here in parametric is exactly the same. Just take your formula and multiply it by cosine to get the x. Take your formula and multiply it by sine to get the y. Okay? It's breaking it into its components. The only difference is this hypotenuse is not a fixed value. It's a formula. So you might have one point here, and then the next time you have a point here, and then maybe here and here. Maybe your graph is some kind of curve. So the radius is constantly changing. That's why this is a formula, not a specific number. If it was a fixed number, it would be a circle. It would be a circular shape. But this is definitely not a circle. So let's graph that and see what it looks like. Okay, but we've answered the question. We've converted polar to parametric. Okay, so I'm going to type in 7 sine 2 theta. Okay, and I'm going to do zoom 6. Okay, so we get this kind of
Butterfly.
petaled. Okay, yeah, it could kind of look like a butterfly.
His name's Daisy.
Let me change something. So yeah, it looks kind of like a flower. And how many petals does that one have? It has 8. What do you think controls the number of petals that it has?
The number.
What number?
4.
The 4. Okay. Basically, if you put in an even number, you get twice the number of petals. So if you put in a 2, you get 4. If you put in a 6, you'd get 12.
Put in like a little.
Now, how about the 7? Let's try changing that. Let's make the 7 a 3.
Just gonna make it smaller scale.
Anybody think they have a guess exactly what that
That's multiple.
3 is? What it did?
It's like a, what's that called? Stretch.
So it did make it larger or smaller, and the 3 is actually the length of something in that picture.
Each pedal?
Each petal. Yep.
Cool.
So
No radius.
if you measured the length of that petal, this one would be 3. Now, what about if I put an odd number? What do you think, like if I put in 3? What do you think I'll get here?
I think it's gonna look cool. Maybe.
Based on what we did, what would you think happens? You'd think it would be 6 petals, but it actually is a little different for odd and even. Odd, you get exactly the number you put in.
Do like 73.
Okay, so odd, you get the same number. Even, you get the number doubled. So it would be kind of hard to do 6 petals, because if you type in 6, you're going to get 12. If you type in 5, you get 5. If you type 7, you get 7. So you'd have to think, I'm not really sure if we can get 6 easily. Okay?
What if you type in like 1 point?
If you type in a decimal, then sometimes it kind of rotates it, or it starts to look kind of funny. It's like if you,
Yeah, don't put 73.
so if you type in like 2.5, you do get 5 petals, but they're not evenly spaced. So based on that, if I type 3.5, how many petals do you think I would get? Yeah, I should get 7, but they're not going to be nicely spaced. Yep, I get 7. So yeah, I take that back. We can get 5 and 7, but you could also get 5 and 7 like this. If you wanted 7 evenly spaced, you could just type that in. Now, how come the petals look kind of, they should be rounded? What's controlling the fact that they're not rounded?
The step.
The step. Okay, my T step, it's 7.5. That's kind of big. If you set it to 2, now it's going to take a little longer, but they're going to look perfectly shaped the way they should. So the more petals you put, the higher you have to make your T step to get a nice, nice picture. Okay, so in general, anything of the form a sine 2 theta, okay, that's what we call a 4-petaled rose. That's what they call it. And the length of each petal is the absolute value of the number in front. Okay, now you could try cosine. If you think about what's the difference between sine and cosine again? It's just a shift of 90 degrees, which when you're doing polar corresponds to a rotation of 90 degrees. So if I type, let's look at 4 theta. Okay. Notice where the petals are right now. Did I type 4 theta? Oh, I meant to type 2 theta. Let's do 2 theta. Okay. So notice the petals are right on kind of like the 45-degree mark for the axis. Okay. Watch what happens if you do cosine. Yeah, now the petals are going to be right on the axis. They've rotated a little bit. Okay, it's still the same idea though. Okay, each petal, this actually I think you can see this clearer. Each petal is 8 units long, and if you count, 1, 2, 3, 4, 5, 6, 7, 8. It's a little harder to see when it's on a 45, but that's the length. Okay. Any questions on that shape? Okay, so that's another shape you're going to see come up in polar. And the last shape we're going to look at is a spiral. Okay, we looked at spirals in parametric. This is a spiral in polar. Okay, so what I want to do is graph this spiral. And I want to use different theta min and theta maxes. Okay, so let's start with just typing it in. R equals theta. So this is a problem where the radius equals the angle. So the bigger your angle, the bigger your radius. So it's going to spiral. Now, how many times would it spiral if I go from 0, well, I'll do it in radians, 0 to 2 pi? Yep, I would just get one spiral. And what would be the biggest my radius would get over the interval 0 to 2 pi? Well, think about if your radius is always equal to your angle. The biggest the angle is going to get is 2 pi. So the biggest the radius is going to get is 2 pi. Anything else I want to adjust? Because if I do this, I'm going to get a really lousy picture. The step, yeah, that's awful. If you're going from 0 to 6 and you go by 2's, you're only going to graph 4 points. 0, 2, 4, 6. So your spiral is going to look, it's going to look like 4 line segments. It's not going to look like a spiral at all. What would be a good step?
0.5, maybe.
0.5, you could even do 0.1 because you're only going 0 to 6.
Oh, yeah, true.
So if you go by 0.1, it's going to graph it pretty fast. And you get one spiral. Now, if I go 0 to 4 pi, how many times is it going to spiral now? You're going to get 2 spirals. Is it going to trace over what it already did?
No, because it moves further.
No, because the radius is just going to keep growing. Right? It's just going to get bigger. What's the biggest my radius is going to be now?
4, 5, 6, 6, 3, 7, 6.
Now, what's going to happen, where is that radius going to occur? Like, what?
Where the last one was.
Right, where it ends, because it's spirals. So the biggest part of your picture is always on the, you need the most room on the positive x-axis. Okay? The other axes you need to zoom out a little bit, but not as much as the positive x. But if you want to make it simple, just set everything to like, see, everything would be on the screen here, I think, except for x max. Now it will be. Y min needed to be a little bigger too. So make that a little bigger. And now you can see the whole spiral. Hey, we get 2. If I went 0 to 8 pi, how many revolutions would I get there?
More after that. Or wait, 2 extra.
2 more, yeah. I would just spiral 2 more times, and my radius would go up to about 25. 3 times 8, roughly. So it would just spiral a little more. Let's try graphing it like putting a negative 4 pi. Okay, so here's 0 to 4 pi. Just save that. What do you think is going to happen if I go negative 4 pi to 0?
It's just going to flip it.
It's going to flip it? Let's try it.
Just like it flattens it over, so.
How many spirals am I going to get? Still going to get 2.
Oh, it did it.
Just going all the way.
Yeah.
Yeah.
It's good.
It's going. Now the picture,
It graphs it different, like it
it graphs it differently. But the picture is exactly the same. Does everybody see it? It's kind of one of those things you can only notice it when it's drawing. But what direction is that being sketched in?
Left or right?
Clockwise or counterclockwise?
Counterclockwise.
Yeah, it's going counterclockwise. Okay, set it back. Let's go. What was it about negative 12? So let's just go 0 to 12 or 0 to 13. Now, what direction is that one going?
That's going counter.
Still going counterclockwise. So what was the difference?
Start.
where it started. So it's the same graph, it just, where is it starting the sketch from? That's all. Okay? It's kind of one of those things, if you had two calculators, you could see it at the same time. Okay? But it's the same picture. Yep.
Can you see the actual equation in that? Like, obviously.
The actual equation? Yeah, it's just R equals theta.
Oh, what's the window?
The window that I used for the last one, that was about 4 pi. I just rounded it off. It's 12.56. Okay, and stepping by 0.1 would be okay. What if you stepped by 1?
Yeah, it probably wouldn't look like a spiral.
Yeah, it's going to look a little bit more jagged on the edges. So you get the idea that it should be a spiral, but that's not enough detail. Okay, so any questions on those graphs? Cardioids, spirals, the rows, different petaled rows. So I might ask you, like, what would be the equation of a rose that has 8 petals with a radius of 5? So you put 5 cosine 4 theta, because it doubles the number of petals, and the number in front is your radius. Yeah?
I was just going to say, how are you graphing the petals on there? Because I tried it, it's still graphing something.
The petals? Well, there's actually 2 ways we can do it. You can either type in 7 sine 2 theta if you want to do it in polar, or you can type what I have below in parametric. It's easier if you do it in polar. It's less stuff to type in. I need to go from 0 to 360, or 2 pi. And stepping by 0.1 should be fine. And the length of the petal, it's going to look a little small, but you'll see it. Oh, actually, that's not too small. And that's it. So that's doing it in polar. Let me put that right here. Okay, if you did it in parametric, okay, let me put this picture here just so we have it. I can't. Just remember what that looks like. There's your petals. If I go to parametric, and now type in exactly what I have right here, 7 sine 2t, cosine t, and then below it type 7 sine 2t, sine t. I should get exactly the same picture I just had if I set everything correct. Parameters is 0 to 2 pi. That should be good. So if you remember what it looked like before, that's exactly the same thing. That's parametric. The other one was polar. Okay. Any other questions? All right, so the homework tonight, same page as last night, 493. And it's 19 through 21, okay, that's all. And then 24, 30, 31, 33, and then the rest is just odds. 33 to 41, and 43 to 40. Actually, I guess I could just say 37 through 47.
Yeah, odd.
I must have changed something. 37 to 47, odd. Okay, so we'll look at that tomorrow. I'll be after school today if anybody needs extra help. And don't forget, we have our first test of term 4 tomorrow.